Well, in Chapter 11, we're going to continue our discussion of hypothesis testing. In this chapter, we'll cover two samples. So we'll cover the formulas for creating a hypothesis test scenario for two samples when we know the population standard deviation, two samples when we don't, and two proportions, and then we'll also discuss dependent and independent samples for hypothesis testing. Again, as I just said, in this chapter we're going to be comparing the means of two different samples. So when we're comparing the means of the two different samples with hypothesis testing, we're going to begin assuming we know the population standard deviation. However, it's important for us to understand that each of these means will come from two different populations. So here's an example that we'll step through to help us understand two-sample hypothesis testing. All right, for the hypothesis testing examples in this chapter, we're going to be following Keisha. She's a new administrator at a hospital, and she's very interested in maintaining very high patient satisfaction ratings for the hospital. So to begin with, she wants to compare day shift nurses and evening shift nurses. She thinks that there might be a difference between the two. Well, she's coming into a situation where this research has already been done, and she's been told that there is no difference between the two. She's also been told that the standard deviation between these two populations is 0.2. But she's going to test out this hypothesis on her own. In her training to become a hospital administrator, Keisha has taken several statistics classes, so she's very familiar with the 5-step hypothesis testing procedure. So she's going to go through those. So step 1, she's going to state the null and the alternate hypothesis. Because she thinks that the night nurses have a higher satisfaction rating than the day shift nurses, that's going to be her alternate hypothesis. So her alternate hypothesis is the night shift satisfaction ratings are greater than the day shift. The null, which is assumed to be the status quo, assumed to be true, is that the night shift is actually less than or equal to the day shift ratings. Step number 2, select the level of significance. Keisha selects a 0.02 level of significance. That gives her only a 2% chance of making a type 1 error. Now, step 3 is to determine the test statistic. Because she has historic population standard deviation levels, she's going to use the Z distribution. Next, step 4 is to determine the critical value. This is a one-tail test. She's only checking one direction. So the Z-score, that equates to 48%, 2% in a single tail, 48% of the area between the mean and the critical value will end up with a critical value that's very close to 2.055. All right, here we're seeing on the normal distribution table how Keisha came up with the critical value of 2.055. We're looking for an area of 0.48. That area does not exactly exist, but we can see that it is between 2.05 and 2.06, and so we'll average the two together and come up with a critical value of 2.055. All right, the 5th step is to take a sample, compute the test statistic, and make a decision. So, Keisha randomly surveyed 25 patients, and she asked them to rate their day shift nurses. She found another randomly selected 30 patients and asked them to rate their satisfaction of their night shift nurses. Well, the mean for the day shift turned out to be 4.55. and the mean for the night shift turned out to be 4.7. So at first glance, she's thinking maybe that her hunch is correct. So she decides to go ahead and compute the Z-score and make a decision. So we see the formula for computing the Z-score. It is simply the sample 1 mean minus sample 2 mean. We'll typically use the larger mean as sample 1 just so that we don't end up with a negative value. Then we divide that by the square roots of the variance and the sample sizes. We then end up with a computed Z-score of 2.77. So here's a visual representation of what Keisha has discovered here. She has computed a Z-score of 2.77, and looking at the normal curve, that is larger than the critical value of 2.055, and so that is indeed in the rejection area. So in this case, she will reject the null and possibly conclude that the night shift nurses are possibly better. Outside of the classroom and using textbooks, you'll often be doing your own research. And when you're doing your own research, you probably will not have population standard deviations to work with. So in that case, you'll use the t-stat, or the t-distribution. So in this case, let's go ahead and assume that Keisha doesn't really trust the population standard deviation that she's been given. And so she decides to compute the standard deviation and the t-test based on the samples that she's computed, not on the previous research that someone else has done. All right, to get the process started, Keisha is going to go through the 5-step hypothesis testing procedure. And step number 1 is to state the null and the alternate hypothesis. The null hypothesis, remember, is what's assumed to be true, the status quo, and that the night shift satisfaction ratings are less than or probably equal to the day shift. Her alternate, the one she's really wanting to test in this case, is that the night shift satisfaction ratings are greater than the day shift. Number 2, she selects a level of significance. She selects 0.05 level of significance. That gives her a 5% chance of making a type 1 error. And step number 3, determine the test statistic. And because she does not trust or have the population standard deviation, she's going to use the t statistic. All right, for step 4, Keisha is going to determine the critical value or the decision rule. Well, it's a one-tailed test, so she's only checking in one direction. And remember that the t-distribution requires degrees of freedom, but with 2 samples, we determine the degrees of freedom differently than we did with 1 sample. Remember before it was simply n minus 1. Well, in this case, you add the sample size for the first sample to the second sample size, and you subtract 2. So in this case, because she had 55 individuals that she surveyed, the degrees of freedom is 53. Now you can use the table, or as I like to do, use Excel. You see on the screen here an example of the t.inv and how it's used to determine a critical value of 1.64. If you do use Excel, notice that there is a negative minus sign at the beginning of that function. That will just return a positive critical value instead of a negative critical value. All right, step 5 is to take the sample and compute the test statistic, and then make a decision by comparing the test statistic you compute to the critical value. Well, computing a t-score manually from 2 samples is fairly complex. We're going to go ahead and step through it. As you probably would have guessed, I like to use Excel to do it, but bear with me as we try to explain how this actually can be done manually. All right, since we don't know the population standard deviation, once again we're using the t-stat. And to compute the t-stat with 2 samples, the first thing we have to do, it's integral to the formula, is to compute the pooled variance. Now the pooled variance, as you can see here, the formula is simply the sample size for sample 1 minus 1 times the variance for sample 1 plus the sample size for 2 minus 1 times the variance for sample 2, and we divide that essentially by the degrees of freedom, n1 plus n2 minus 2. Now after we have the pooled variance, we're then able to go ahead and compute the t-score. And so you see the formula on screen for computing a t-score on your own. You have the 2 sample means, x bar 1 minus x bar 2, and you divide that by the square root of the pooled variance that you computed earlier times 1 over the sample size of 1 plus 1 over the sample size of 2. All right, we're ready to use these formulas with the values that Keisha computed. And I just want to point out one thing, because we really are looking for a greater than. We want a positive critical value, positive t-stat. We're going to put the sample with the highest mean as sample 1. Okay, so once we've done that, we want to compute the pooled variance. So we take 30 minus 1 times the variance for sample 1 plus the 25 minus 1 times the variance of sample 2, and we divide that by the sample sizes of each and subtract by 2 the degrees of freedom. We end up then with a pooled variance of 0.19478. Once we have that, we can fairly easily compute the t-stat. So we take sample size, or excuse me, the sample mean for sample 1, subtract the sample mean for sample 2, and we divide that by the square root of the pooled variance multiplied by 1 over the sample sizes. And we end up then with a manually computed t-stat of 1.1488. So this is really the second time Keisha has run the same numbers, but the computed t-stat that she computed is 1.1488. That is less than the critical value for the degrees of freedom that she computed, and the level of significance that she selected of 0.05 of 1.674. So she will not reject the null hypothesis. So using these values, she cannot conclude that night nurses have higher satisfaction scores than day nurses do. Now, when she did this with the z-stat, she was able to reject the null hypothesis and perhaps conclude that the night nurses were better. However, using the t-stat, she was not able to do that. Well, the reason for that is the population standard deviation was significantly different than the sample standard deviation that she computed, and that value does make a difference in these formulas. As I've mentioned many times in these videos, I really do enjoy using Excel for statistics. And Excel's data analysis add-in has a t-test option that very easily computes a t-stat from two different samples. Now, if you're working with the data analysis and you have it turned on, I will have videos on my website that will explain all these things. But from the data analysis, you would choose t-test two sample assuming equal variances. Now, even though the variances weren't exactly equal, they're close enough that they're not statistically different, and we'll learn a little bit more about analyzing variances in an upcoming chapter. So, t-test two sample assuming equal variances. All right, the next step is to simply select the ranges that contain the variables that you're looking for, the two samples, and then you put in the alpha, which is in this case a level of significance. And when you click OK, you'll get a really cool outcome of the t-test analysis. And notice that it gives you the t-stat, and it also gives you the p-value for both of the one-tail and the two-tail test. And remember, we were only doing a two-tail test, so our t-stat of the 1.149 and the p-value associated with that t-stat is 0.1278. Keisha's getting just a little bit confused. She did a hypothesis test using the Z statistic, and she was able to reject the null hypothesis and potentially conclude that the night nurses had better satisfaction ratings than the day nurses. But then she decided to run it as a t-stat. Well, this time, with the t-stat, she was not able to reject the null and could not conclude that the night nurses were any better. So she decides to try another method. She is going to try a proportion. So what she's decided to do is ask every patient or randomly survey some patients, and they are simply going to answer a question, yes or no. She's going to ask them, were you satisfied with the services you received at the hospital when they were discharged? They could only answer yes or no, because remember, with proportions, that's what we're working with. One of two choices, yes, no, pass, fail, dead or alive. So let's go ahead and see how this shakes out. All right, once again, we're still doing a hypothesis test, even though we're working with two sample proportions, so we have to go through all 5 steps. Step 1 for Keisha is to state the null and the alternate. This time, she just wants to determine, is there a difference? And so the null hypothesis, what's assumed to be correct, is that there is no difference between patients who are satisfied with their day shift nurse versus patients and the satisfaction rating for night shift nurses. The alternate hypothesis is simply that there is a difference. Step 2, select the level of significance. Keisha has decided once again on a 0.05 level of significance, giving her a 5% chance of making a type 1 error. Step number 3, determine the test statistic. Because we're working with proportions, we will use the Z distribution. Step number 4, determine the critical value or the decision rule. Well, we pretty much almost have this one memorized here, but it's a two-tail test giving us both directions that we're looking for with a 0.05 level of significance. Each tail in the curve has 0.025. Well, we're looking for 0.475 between the mean and the first critical value or the tail, and that gives us the critical value that we've used quite a bit before, 1.96. All right, so we're ready for step number 5, which is to take a sample and compute the test statistic. Well, Keisha surveys 55 patients that have been recently discharged, and she finds 25 that were discharged by day shift nurses and 30 that were discharged by night shift nurses. The resulting proportions are as follows. The day shift discharged patients that were satisfied were 20 out of 25. The night shift discharged patients that were satisfied were 25 out of 30. All right, we're ready to compute the z-stat for two sample proportions. Like the t-test we computed a moment ago manually, it also is a two-step process, but it isn't as difficult as what we had to do with the t-stat. So the first step is to compute the pooled proportion, and the pooled proportion is simply the overall proportion. It is the number in sample 1 that answered yes, plus the number in sample 2 that answered yes, divided by the total sample size. So our pooled proportion equates to a value of 0.8182. Now to compute the z, once we have the pooled proportion, we take the proportion for sample size 1, we subtract the proportion for sample size 2, and we divide that by the square root of the pooled proportion, and times 1 minus the pooled proportion divided by the sample size. You can see the formula there. Well, what are we going to end up with? So we compute a z-stat for two sample proportions of 0.31884, and that falls within the do not reject because it is not greater than 1.96 or less than negative 1.96. So once again, she will not reject the null hypothesis, and she'll conclude, based on this limited survey, that the satisfaction ratings between the patients that have been discharged by day and evening nurses are equal. All right, just a visual representation of what we did here. The z-score that we computed was 0.31884, and that definitely falls in the do not reject area because it's not in the tails. It's not greater than 1.96 or less than negative 1.96. Well, now we need to introduce the concept of dependent samples. Up to this point, the samples that have been discussed have been independent samples. They're not related to each other in any way other than they're in the same hospital. A dependent sample, on the other hand, is the same individual surveyed twice. So, for instance, maybe we're looking to see if a new vaccine works. So we would test the individual before they got the vaccine and then sample the individual after they got the vaccine. So we're typically looking for a before and after. And the after is usually after an intervention such as a medication, behavioral adjustment, or some sort of training. So with all the hypothesis testing that Keisha has done up to this point, she's pretty much given up on the idea that one shift of nurses, either day shift or night shift nurses, have better satisfaction ratings than the other. So now she's deciding, well, maybe we can just improve them all together, all around. And so she's going to go ahead and provide training on customer satisfaction, patient satisfaction, and then she's going to test and survey nurses before the training and after the training. And so she's going to randomly select 10 nurses before the training, give them a week after, and see how their satisfaction ratings do after they've taken their training. Once again, we go through all 5 steps of the hypothesis testing procedure, the null and the alternate. And so the null is that the training doesn't make any difference, that the satisfaction ratings after the training are actually going to be less than or equal to the ratings before the training. The alternate, which is really what she's trying to find out, is that the satisfaction ratings after the training are better than the satisfaction ratings before. Once again, she's going to select a significance level of 0.05, giving her a 5% chance of making a type 1 error. And she doesn't have the population standard deviation, and so she's going to use the t distribution for these dependent samples. All right, we're determining the critical value. And again, just a reminder, a dependent sample is the same individual once before the intervention and a second time after the intervention. So it's a one-tailed test because she's simply wanting to check greater than or less than or equal to for the null. The sample size is 10, even though there were 20 surveys given. So still, with a sample size of 10, the degrees of freedom are 9. And so with a one-tailed test, degrees of freedom of 9, 0.05 level of significance, the critical t-value is going to be 1.833. All right, step number 5 is to take a sample and compute the test statistic. And we're back to the 1 through 5 survey level of satisfaction rating that she's given to the patients. And so here we have each of the 10 nurses and their overall mean satisfaction rating before the intervention, before the training, and then after the training. Right, the formula to compute a t-stat using dependent or paired samples is what you see on the screen here. The D with a little hat is the mean of the differences of the means between before and after the intervention. We're dividing that by the standard deviation of the differences. You see the formula for that. It is the square root of the sum of each difference minus the mean of the difference squared divided by n minus 1. And we'll see on the next screen how we can actually compute that in a worksheet. All right, here's how we can compute the t-stat. I've kind of laid it out in each individual and their value, the rating before and after. And in column D here, we're computing the difference. And then in column E, we're taking the difference minus the mean of the difference, and we're squaring that. We have a mean difference of 0.26, and finally we have the standard deviation of the differences of 0.38644. Once we have all these values, we're able to have the mean of the differences, which is 0.26, divided by the standard deviation of the differences, 0.38644, divided by the square root of the sample size. We end up with a computed t-stat of 2.128. That is larger than the critical value, and so Keisha is going to reject the null hypothesis and conclude that finally she's found a way to increase patient satisfaction, and that is through nurse training. All right, Excel's data analysis tool pack, as you might have guessed, has a way to do this very easily. Within the data analysis, the feature is t-test paired to sample for means. Once you select that, click OK. You're then going to select your variable ranges 1 and 2. And as we've seen before, to avoid a negative t-stat, it's a good idea to put the larger value as variable range 1, which in my case is the nurse case was the after training. So that would be variable range 1, and then the before for variable range 2. The alpha, the level of significance 0.05, and we click OK, and we see the result. All right, so this is the output that you would see after you click OK, and with the paired to sample for means, we see quite a bit of information that Excel's computed for us. We have the means for each, the before and after. We have the degrees of freedom of 9. We have the t-stat that it computed of 2.12762. We also have critical t-values for one-tail and two-tail. This was a one-tail test, and so the critical value of 1.833 is smaller than the t-stat we computed, so we will again reject the null. We can also use the p-values to determine that as well. Our level of significance was 0.05, and for a one-tail test, the p-value that Excel computed is 0.03, which is smaller than the 0.05 we wanted. So we really have a 3% chance of making a type 1 error. And instead of looking or comparing the t-stats to the critical value, you can also look at the p-value. And if it is smaller than your level of significance, then you can also conclude to reject the null hypothesis. All right, here are some of the highlights from Chapter 11. As we've seen, with a variety of statistics, test statistics that we're working with, we're still going to use the 5-step hypothesis testing procedure. And that 5-step procedure is, number 1, state the null and the alternate. Number 2, choose the level of significance. Number 3, determine the test statistic. Number 4, locate the decision rule, the critical value. Number 5, take the sample, compute the test statistic, and make a decision. And as we've seen, there are multiple formulas that we will use to compute the test statistic. Well, here are some of the formulas that we used in this chapter. To compute a z with 2 samples, we see the formula there on the screen. When we do not know the standard deviation, we're going to compute a t. We saw that that was a rather complex formula in which we had to pull the variance first. We also saw that we could use Excel to compute many of these. And here are some additional formulas that we used in this chapter. We computed a z for 2 sample proportions. We had to pull the proportion to do that. We also computed a t-stat for dependent or paired samples. Remember that with a dependent sample, it's the same individual being surveyed twice. We also have the formula for computing the standard deviation of the differences. And I do have a definite opinion about memorizing formulas, and a lot of stats teachers won't agree with me, but check out my video on formula memorization commentaries, and you'll get my idea on that. And remember, all of these lessons are based on my textbook, Surviving Statistics, which is available on Amazon. And do remember to check out my website for downloadable files, calculators, and other resources.